Welcome everyone to this Drug Discovery World webinar entitled The New World of Allosteric Modulation, a dimmer switched for GPCR agonism and antagonism. As we well know, GPCRs are nature's prototypical allosteric protein, and all functions of these proteins involve the transduction of ligand-induced conformational change to a third body. There are new ligand properties that can be determined through the application of allosteric theory to GPCRs that can greatly expand knowledge and predictability of drug candidate effects. One of the main properties is probe dependence, whereby GPCRs are now seen not to be mere switches, but rather microprocessors that can receive different signals in and yield different signals out to the cell. To explain this further, I am delighted to be joined today by Professor Terry Kanakin from the Department of Pharmacology of the University of North Carolina School of Medicine. Dr. Kanakin has been involved in drug discovery for over 30 years. He received his PhD in pharmacology at the University of Alberta, Canada, followed by a postdoctoral fellowship at University College London in the UK. Dr. Kanakin worked in drug discovery at the old Burroughs Wellcome before serving 25 years at GSK, and has been renowned for his work on drug receptor theory and allosteric protein function. I'm Robert Jordan, publisher and editor-in-chief of Drug Discovery World, DDW, and I'm going to serve as your moderator today. Hopefully, we will have plenty of time for a Q&A session at the end, where we will be joined by Dr. Neil Charter and Dr. Thierry Hollas. Neil obtained his PhD at Imperial College London and worked as a scientist at UC Berkeley for 7 years before joining Discoverex, which is now part of our sponsors, Eurofins Pharma Discovery Services. Thierry is a study director in charge of standard and custom in vitro pharmacology studies at Eurofins Pharma, and he's responsible for a portfolio of more than 150 companies, including 8 major pharma. Thierry came to Eurofins from Schering-Plough and received his PhD from Pierre and Marie Curie University in Paris. So at any time during the webinar, you can send in your questions for our panelists by writing your question in the Ask a Question box and pressing OK. Naturally, we will try and answer as many questions as time permits. Okay, I think we're ready to go. So if you're sitting comfortably at your screens, let's get started. Okay, so Terry, if you're ready, the floor is yours.
Hello, and welcome to a webinar on allosteric drug function. I am your speaker. My name is Terry Kanakin. I'm at UNC School of Medicine, but I am giving you this webinar from the point of view of chemists and biologists moving forward allosteric compounds for potential drug candidate status. Our drug target are G-protein coupled receptors, GPCRs, conveniently located on the outside of cells, controlling a myriad of cell functions. These have long been regarded as low-hanging fruit for drug discovery. However, about 15-20 years ago, this low-hanging fruit started to reach limits. That is, the field was starting to be mined out, simply making copies of hormones, transmitters to produce responses from these targets, or molecules to inhibit their function, did not yield unique therapeutic compounds as they once had. However, during this period also an allosteric wave has hit pharmacology, probably because we were screening more and more with functional assays, and these assays can see allosterism as opposed to just steric hindrance. So we started to see allosteric molecules enter the field, and this completely changed discovery. What do I mean by allosteric molecules? Molecules with a very different pattern of activity than standard steric hindrance type of binders. These are compounds that bind to their own site on the receptor, modifying it in various ways to produce biasing in terms of the signals they can produce, slightly reducing activity, even increasing activity, and so you have the potential to potentiate failing systems. So it completely changed what we thought of in terms of possible drug targets. Bias and allostery was starting to be considered as another shot on goal. Targets that were intractable, targets that were mined out, could be revisited, and so the whole field has been revitalized by the entry of allosterism, and that is what we will be talking about today. So I will center on the unique features of allosteric interaction with receptors, and then the new kinds of molecules that emerge from these studies, and importantly the assays that you need to use to quantify allosteric activity and predict activity in a range of tissues. When I talk about allosteric activity, I'm thinking of something like this: compound 38 binding to its own site on the M1 receptor to modify the activity of that receptor to the natural transmitter acetylcholine. And so allosterism basically is quite new to the discovery process. If you were to look at the number of papers that cite allostery or allosteric and count them in PubMed, you see this kind of curve here with years. We see the early years, there's not much mention of allostery. One idea that has been put forth to explain this is that we were screening orthosterically at this point. Most screens were binding assays looking at steric hindrance, and so they would no doubt miss an allosteric compound like the one shown here. This is an inhibitor producing non-competitive inhibition of glutamate, as you see on the curves on the left. But this compound also does not affect glutamate binding in any way. So a binding assay, binding screen, would not see this compound at all. However, in the years after 1990, more and more functional assays were being used as screens, and we started to see a tremendous increase in the allosteric molecules. And of course, function is the important aspect of drug action, much more important than binding. So this really changed the face of discovery. We had changed how we were screening. We were changing the kinds of compounds we were seeing as hits and leads, and it was basically a revitalized world for GPCRs. And so generally you could support this statement at this time, whether your program seeks an allosteric molecule or not. If you are running a screen, there's a very good chance you will get an allosteric hit or lead, and so it probably behooves us to understand how to handle this kind of compound and how to quantify its activity. Allosteric molecules basically see receptors for what they are, shape-shifting proteins, and they can form many shapes, and in any one instance you can see what is referred to as an ensemble, a collection of states slightly different in shape of about equal free energy. So drugs interact with these ensembles binding to certain states, not binding to others, and thereby changing the ensemble. Therefore, you might see a picture as shown on the left, where the cell is responding to a collection of spontaneous states, not all of them signal, but they are different. Then we add a drug, and it makes some states stable at the expense of others, and now the cell is responding to a totally new ensemble. And it is how complex these ensembles are that leads to the tremendous variation in possible allosteric action we can see with these new molecules. So the receptor has gone from a switch giving us one single signal of varying strength to what it really is. It's a microprocessor taking in different kinds of signals in and giving us different kinds of signals out. In fact, receptors are nature's prototype allosteric protein. Everything the receptor does is allosteric. We can show that through looking at what is called an allosteric vector. So the allosteric vector here is the compound in red, receptor protein, and a signaling protein. And where we aim this vector defines what kind of function we are talking about. If we aim the vector towards the cell, we are producing response. If we aim the vector along the plane of the membrane, we are looking at dimerization. If we are talking about two binding sites on the receptor, we're talking about guest allostery. But in all cases, it's allosterism with a range of potential states. What that also teaches us is binding is not a passive process. Here we have a correlation based on the probability of docking molecules to an ensemble. And what I'm showing here is the affinity of every compound in the library is correlated with a different efficacy. That is, just having different affinities for different states will change the ensemble, and that is regarded as an efficacy. So when we bind a compound to the receptor, it's not just a passive binding giving us a protein with that compound on it. It is a different receptor. No matter how small a compound is and how large a protein is, that protein will perceive it. Its energy will change. And so we have a potential efficacy. This has really changed as well the way we view discovery and the screening process. Before, it was thought that, of course, all drugs bind, and some are special. They have efficacy, we see response. This limited view of efficacy simply came about because we had limited assays to see what response was. Now that we have many assays to see the various behaviors that receptors can give us, and knowing that binding is not a passive process, it is an active process, you could make the point that you could almost argue if anything binds, they have the potential to have efficacy in some way. All drugs have efficacy. Well, what this does is it changes the way we view screening. Before, we would run a screen, take our hits, and move on. Now, every compound that binds in our screening assay potentially has some sort of efficacy, and it should be tested in every possible kind of assay to detect this. If we consider, again, efficacy as simply the way the molecule causes the target to change its behavior to the cell. So now let's consider how allostery fits into this view. I'm going to zero in on three ideas here. What makes allosteric molecules so special? Well, the first thing is they can completely change the very nature of the receptor. They can change efficacy, signaling, and so forth. Because an allosteric compound binds to its own site, whatever it does will stop when that site is full. And so you have the potential to modulate, not completely inhibit, but just reduce activity or even increase activity. So you have a much broader scale to adjust receptor activity. Finally, all allostery is probe dependent. What this means is the effect occurs through a change in shape of your protein, and so if you have two probes binding to the protein, there's no rule that says that the change in shape will be equal to each probe. In fact, the rule is that it rarely is. This is called probe dependence, and it can really be useful therapeutically. So let's go into these ideas a little bit more before we start talking about allosteric molecules. The first is changing the very nature of the receptor. An allosteric molecule can alter the affinity of a compound for a ligand through a term called alpha, and so it can increase it or it can decrease it. And an allosteric compound can also alter the efficacy of a compound through a term beta. This can increase or decrease as well. So depending on what alpha and beta are, we can get a whole range of effects. For example, a very active therapeutic area are positive allosteric modulators, so-called PAMs. These increase responses to a natural transmitter or a hormone and are often used to replace therapy in failing systems. This can happen because the allosteric compound binds to a site other than the natural hormone or transmitter, so it still allows it to bind. So what we are looking for here is that curve in the heavy line there, which is the control, will shift to the left, maximal increase going up, and so the activity in an assay would be shown by the increased red dot response. These can reflect, as I mentioned, revitalization of a failing system or potentiating a beneficial response. So let's take an example of a PAM used for therapy, in this case GLP-1 for diabetes. GLP-1 causes an increased release of insulin, which can be beneficial in diabetes. Why would a GLP-1 PAM be better than a simple GLP-1 compound that activates the receptor? The main reason is a GLP-1 PAM will not do anything until GLP-1 is present. And in this case, GLP-1 is released when you eat a meal. And so you would only have the effect, the signal, when you eat a meal, and you would have an intermittent therapeutic event. Presently, GLP-1 agonists are used, but they activate the receptor 24/7. They're constantly present, and this causes severe nausea. So the hope is that a GLP-1 PAM would reduce nausea because of its intermittent action. It would also presumably reduce desensitization. It would preserve complex pattern of response. Allosteric compounds are also good ways to get drug-like molecules for peptide receptors. So as I pointed out earlier, there are two ways to increase response. You increase the affinity through the term alpha. So if alpha is greater than 1, you see a shift to the left of the curve. Or you can increase efficacy beta. You see an increased maximal response. Most often you need an assay to differentiate these effects because you want, probably for a failing system, you want to have a beta response. If you had a PAM that potentiated affinity, you would simply increase the very small amount of remaining response present in a failing system. What you need to do is increase the efficacy of what already is there. And so diseases, you need an assay that'll tell you you have a beta PAM as opposed to an alpha PAM, and this speaks to the kind of assays that are used, and we will talk about those a little bit later. Beta PAMs are extremely powerful, however. Let me show you an example of what they can do. This is work from Katie Leach, where she shows how you can revitalize a failed receptor through a beta PAM effect. What we have is a mutated M4 receptor such that it is completely unresponsive to acetylcholine. As you see there, no curve. You can then come in with a beta PAM, in this case Lilly's compound 298, and you actually bring the receptor back to full natural function. So you can see these can be extremely powerful therapeutically. Secondly, because of the separate binding sites, you can adjust allosteric activity to a fine point. So here we have an example of that. We have the acetylcholine curves in a cardiac muscle preparation, shifting to the right to the allosteric negative compound algironium. And as you see, you inhibit acetylcholine, but you don't completely inhibit it. What you've done is you have reset the sensitivity of the receptor to acetylcholine, but you haven't completely inhibited it. This can be extremely useful, and that curve stops because the binding site for the algironium is full. You can also see that with binding. Here we have the CCR1 receptor binding the radioactive ligand MIP1 alpha. You can displace MIP1 alpha with the cold ligand completely. The allosteric compound UCB, however, does not completely displace. It is not displacing, it simply resets the affinity of CCR1 to MIP1 alpha, reducing it a bit, but still letting the receptor respond to the chemokine. So you have a reset, in fact, of the protein. This can be extremely useful therapeutically. Finally, the third point is probe dependence. This is a very important property of allosteric systems. And let me just go over what that is again. If we have a protein interacting with tracer 1 and tracer 2, and we add an allosteric compound that changes the shape of that protein, there's no rule that says those tracers should be equally affected. In fact, the rule generally is they rarely are, and this is called probe dependence. This can be very dramatic, as in the case of this is the M2 receptor and the allosteric compound aluronium, which decreases the binding of tritiated methyl QNB, but actually increases binding of tritiated atropine. So I have probe dependence shown here. This is the M2 receptor, and what you're seeing is the PEC50 to a range of compounds on the receptor in the absence and the presence of an allosteric molecule. And what you see is the changes produced by the allosteric compound vary with whatever probe is being used, and so we can see that a probe like pilocarpine is potentiated, APE is not changed, and air-choline is inhibited. That is probe dependence. So with that in mind, let us see how these ideas can be applied to the discovery of new drugs, drug discovery in the allosteric world. And I'll talk about two ideas here. First, define systems where allostery can be unique and useful. And secondly, how it is measured and how it is studied in a system-independent way. First, what kind of systems can benefit from an allosteric mode of action? There are many properties of allosteric compounds that really are unique and really set them apart from standard orthosteric molecules that bind to the natural binding site for hormones and transmitters. They can change huge protein-protein interactions. As we saw, we can adjust activity. We don't have to completely turn it on or turn it off. What we'll see is we can therefore modify multiple signals and give fractions of those signals, and therefore change the quality of efficacy. We can also, through probe dependence, change the action of certain hormones without affecting the actions of others. We can limit maximal effect. What this can do is it can greatly increase target coverage. If you have a compound that only produces a 10-fold shift in a curve, you can use a higher concentration in vivo, get a longer duration of action without fear of overdose. Because of probe dependence, you can actually create new efficacies. We saw that with the M4 receptors, and importantly, you can find drug-like molecules for otherwise intractable, such as family B receptor proteins. So this is in fact one of the most important reasons why we are seeing an increase in allosteric screens and so forth. Targets that have not furnished leads the standard way, orthosteric binding, have been rescreened as allosteric screens. One of those, such as GLP-1, and people are starting to see hits where there were no hits. So, let me now discuss some of the new kinds of molecules that we can see through allosteric means. And one of those are so-called biased ligands that can produce different signaling patterns from receptors. We'll talk about those. I've already mentioned PAMs, where we can potentiate failing responses, and this translates also to inhibitors, so-called NAMs, negative allosteric modulators, and with probe dependence we will see how they can be useful uniquely as well. So let's take the first case, biased ligands. What do I mean by a biased signal? If we take a cell and look at those receptors, let's say they are angiotensin receptors. If we activate those receptors with angiotensin, you would generally see activation of GQ protein and beta-arrestin. Bias signals are produced by analogs that produce fractions of that sort of profile. For example, the biased ligand for this receptor, TRV12027, produces only signals to beta-arrestin, not G protein. This is what we mean by bias. Much has been written about it. It is a new and exciting area in discovery. It's treated as being new, but it really isn't. All it is probe-dependent allostery, which has been known for many years. So if we look at those sites for tracer 1 and 2, and we turn them inside the cell and give them names, G protein and beta-arrestin, that is all we mean. We have a biased compound that interacts one probe and does not change the other. There are many ideas put forward for design of improved drugs through biased signals. The other thing this has taught us is that not all compounds coming out of a screen are equal. That is, if they make stable, unique ensembles, then they will have a unique signaling pattern. How is this used in discovery at present? What it used to be is we would run a screen and we would take our most active compounds, and in this case our most active compounds are the filled in circles, and we would advance them to the next assay. Now what you can do is take a broader collection of compounds that interact with your target, and run them in another counter screen, and I guarantee you will see a scattergram. They will not be equal. Now what you can do is put forth molecules that you know are different. These would be the compounds in red. You know they are making different active states of the receptor because they're giving you a different differential activity in the two assays. So these would be the compounds you would push forward, And the idea is these would give you a much better chance of seeing a unique therapeutic phenotype in the next assay than simply pushing forth the most potent compounds that could be doing the same thing. So, let's start looking at some actual curves and some actual data from these kinds of compounds. A compound like our friend the GLP-1 PAM, what sort of activities would we see? Well, actually I'm showing our compound 38 potentiating acetylcholine. So our assay shows the control curve in black in the absence of compound 38, and then in the presence of increasing concentrations of compound 38, we see the curve shift to the left, and we see a small increased maximal response. This is the pattern that the assay needs to give us, and it is this pattern that we will convert into system-independent numbers for the chemist to modify drug activity. So here we have some data from Eurofins of another interesting compound. First of all, on the left we have the PAM BQCA, again showing potentiation of acetylcholine. The curves are shifting to the left. On the right, we see a different kind of allosteric compound for GRM2. We see the curve shifting to the right and depression of maximal response. So here we see an inhibition. This is also a useful therapeutic effect. A word about PAMs and NAMs now. It's the product of alpha beta that determines whether you will see potentiation. If alpha beta product is greater than 1, you will see an increased response, or if alpha beta is less than 1, you will see an inhibition. An extremely interesting new type of compound is shown below that, the PAM antagonist. These compounds increase the affinity of the receptor for the agonist, but decrease the efficacy. So alpha is greater than 1 and beta is less than 1. These compounds still inhibit because those values still end up to be a product less than 1. But why are PAM antagonists so interesting? This is again work from Eurofins showing a well-known such compound, ORG569 for the CB1 receptor. And what you're seeing is this compound actually potentiates binding to the CB1 receptor. So that's the curve furthest to the left. We see an increased binding of the agonist to the CB1 receptor, but on the far right you see in terms of function this compound actually inhibits response, and what you see with the full curves is under that, so we're seeing the curves depressing. Why is this effect useful? Well, in this case, ORG569 has been shown to shuttle the protein into a sterile quaternary complex. Binding goes up, but it's a complex that cannot signal, so function goes down. But the important thing is the positive alpha. What this means is the higher the effect in the system, the more active will be the inhibition. The first such compound reported was a compound called ifenprodil. This is an NMDA inhibitor, and what you see is the curves depress and the EC50 to NMDA actually get better. What this means is ifenprodil is increasing the affinity of the receptor for NMDA. But the important thing here is NMDA is also therefore increasing the affinity of the receptor for the inhibitor ifenprodil. In other words, this compound gets more active the harder you drive the system. This can be an extremely useful property, and these compounds are sought after in therapy as very good inhibitors. They also give very good target coverage in vivo because the presence of the natural hormone and transmitter means that these compounds bind to the receptor for long periods and give very good target coverage. So we can say that PAM antagonists seek and destroy the receptors that are causing signals. They become a most useful therapeutic entity. Okay, I'm going to finish this webinar talking about measuring these effects with assays, fitting to models, and getting system-independent numbers. So in the lead optimization process, we do experiments and we get what is called descriptive data. We see what we see, EC50s and so forth, but the aim really is to convert that to predictive data, because what we want is some measure of activity in all systems. We're not working in the therapeutic system. We want to somehow project what our compound will do in the therapeutic system. The bridge from descriptive to predictive systems are parameters. Pharmacology gives us, and we get those from fitting curves to models and getting these parameters like affinities, alpha, beta, efficacy, and so forth. And so the assay becomes critical. As you see here, the assays really are prisms. What we see are not really efficacies. It's what the assay wishes to tell us about what efficacy is. And it's very important that we use the right assay, that the assay tells us, in fact, what is truly happening and does not obscure this in any way. For example, let's return to our ideas about bias. What kind of assays are run here? Well, here's an example looking at the chemokine receptor CCR5, and we're looking at GQ response in red there, and then looking at the internalization through beta-arrestin binding in blue, and we see the effects of two chemokines, CCL5 and CCL3L1, and we see very different profiles. CCL3L1 gives us much more internalization for given activation of G protein than does CCL5. It is bias. So what we do is we run these assays, we get bias numbers, and we use them in various ways. Currently they're presented as radar plots or clusters where we analyze the effect of chemical structure on bias. Well, we need the assays and we need the models to give us these numbers. This is a very important process. So let's generally talk about models. Models are extremely useful in pharmacology. Every time we do an experiment and in our mind's eye think about what happened, we've already made a model, but the best models have got rules as put forth by Hawking. If we can discuss what happens in terms of an equation, then we can pretty well predict a universe of behaviors from that system, and this can be extremely useful predicting therapeutic behaviors in other systems. So the process runs that we do our experiment, we make our model. Model with equations enables us to make a prediction which predicts the next experiment. We then do the experiment. Does it fit? If not, we modify our model, and it's an iterative process that we keep doing until we're happy enough that we understand what's going on. So if we were to think about what happens in an allosteric discovery program with this, this is the current most simple allosteric model for function, and all it is the Stockton-Elert allosteric binding model tacked on as the front end of the operational model. So we have molecules, say it's a hormone or a transmitter A producing response binding to the receptor, and then an allosteric molecule B modifying that. So you can have A and B binding to the receptor at the same time, separate sites, and so what comes out of this is what is going to happen to the response of A in the presence of varying concentrations of B, and the equation for that, this is the most simple equation you can have, and it's present in programs like PRISM and so forth, is you just fit your curves to this equation, and what you're after are the system-independent measures of allostery, in this case alpha, beta, and if the compound produces response in its own right, there might be an efficacy term tau as well. So what we're trying to give the chemist is we have an allosteric compound, it binds with a Kb, it may have an efficacy in its own right, tau, but it'll certainly have a value for alpha and beta for the natural system, and it is this that we are after to get to give to the chemist for the structure-activity relationship. So here is an example of that process. This is now BQCA and responses to acetylcholine in an M1 receptor system. And what you're seeing on the left are curves to acetylcholine in the absence and presence of increasing concentrations of BQCA. That's what we see. We fit it to the equation model, and in this case what we get are system-independent measures. In this case alpha 12, beta 2, an efficacy of 24%, and a Kb of 5 micromolar. This is extremely useful data because this will be true in each and every system that you put BQCA in. It is not a system-dependent answer. This will predict the total activity of BQCA in all systems. The importance of fitting it to a complex model is shown here. We can get a qualitatively similar profile for BQCA when we use a calcium assay. The problem with calcium assays, of course, is they're a hemi-equilibrium assay, and so they can give you erroneous readouts of response. So here we have the curves in the absence and presence of BQCA. They look all right. The thing is, when you fit these to the equation, it's a very rigorous criteria. You find you cannot fit all the complete sets of curves with one set of alpha and beta value. In other words, the assay is inappropriate. It cannot characterize the true allosteric effect. So in this case, doing that, we see that the calcium assay is really an inappropriate model, and in general, calcium assays are not very good models to quantify allosteric events. If you can get a universal set of alpha, beta, and so forth parameters to fit activity in all systems, you can get a very powerful outcome as shown in this example here. Here we have the action of a PAM, that is, the curve goes from the control curve to the red PAM altered curve in 6 different cell lines. And the only difference between these cell lines is sensitivity. There's an increasing receptor expression. So system 1 has a low expression, system 2 and so forth has a higher receptor expression. And as you can see, qualitatively, you're seeing very different effects on the curve, and this might be confusing if you just zero in on any one system. However, the model enables you to account for this, and what you see is you can fit all of these 6 cell lines to a single set of constants, in this case alpha 2, beta 4, and a 5% efficacy. So when it works extremely well and can give you your chemists important data for structure activity relationship. Well, that takes us to the end of this webinar. What I hope to have shown you is that the discovery world has become very much enriched by the advent of allosteric molecules, and these have come to us courtesy of increasing use of functional assays, especially in screening. When you have allostery, then you can have a great deal of texture in activity, biased signaling, and so forth, and so you have a very rich palette of potential drug candidates. Secondly, you can go to targets that previously did not give you much and basically revitalize them. This has happened for a great many targets, mainly peptide receptor targets for which it has been difficult to get non-peptide hits and leads. Finally, through fitting of curves to models, you can get very complex patterns reduced to very simple numbers. So we can get system-independent numbers that can quantify allosteric effects and give hard numbers for modifying activity. And the key to this is robust and good assays that reflect what's going on. So we have a great deal of number of assays now, more than we ever have had, and it is important to use them all to get a broad spectrum of the kinds of activities that you can look at. So with that, I'll come to an end. I just want to re-stress the importance of the assay is the key to all this activity, and I think we're going to open it up now for questions. Thank you for your attention.
Okay, I'd like to thank Terry for his valuable contribution. Very interesting. I'd like to thank Terry for his valuable contribution. Very interesting. Okay, we should have time for a few more questions. At the end of the day, we obviously have a time situation, but if there are any questions, quickly just fill your questions in, press the send OK button, and we'll answer as soon as we can. Start off with one question to start off with for Terry. What simple assays can be used to characterize an agonist hit from a high throughput screen toward candidate selection?
Agonist hit. Oh, fine. Okay. Basically, you want to have an assay that tells you the affinity, that is, concentrations that start doing something, and efficacy. And efficacy has changed. It used to be a simple thing, one assay. Now, of course, we know we have many assays, and so as many efficacies as the program thinks might be relevant to a profile. And so you get a picture of what your compound's doing, but in this world as well, we need to quantify bias. So we have natural hormones, transmitters that give a certain mix of various pathway signals, so let's say GI, beta-arrestin, and so forth. Synthetic ligands tend to produce bias-type signals, and it's a question of how biased. So it would be a good idea to quantify that. Back in the old days, you would quantify selectivity, and that was generally thought to be receptor selectivity, the outside of the cell. Now we need to, because of bias, we need to quantify intracellular selectivity as well. So you've got that, you've got selectivity in terms of receptors, selectivity in terms of signaling. Another good thing to do is to check and see whether your compound's binding to the orthosteric site or to an allosteric site, because this will determine what happens in vivo. An orthosteric ligand will hijack the target and you will get the profile of the new compound. An allosteric site may be permissive. It may still let the natural system signal, and so you'll have a complex mix. So you have to check that. And finally, if you really have a compound towards the end and you want to expend a bit more work, define whether your potency is efficacy-based or affinity-based. An efficacy-based potency will be much more robust in terms of producing response to more organs than a affinity-based potency.
Excellent, thank you. I have another question here, Bill Clark, Professor Bill Clark, who would like to know, if he understands correctly, should screening for allosteric compounds be done using the endogenous agonist?
Yes. Hi, Bill. Yes, yes, definitely, because of probe dependence. But sometimes you can't do this. For example, some of the early work on Alzheimer, where people were wanting to potentiate acetylcholine, but acetylcholine is a nasty, unstable, sticky, miserable compound which you wouldn't want to screen with. So screening was done with surrogates, stable analogs and so forth, and then you have to check for the natural ligand, and there was a lot of probe dependence that went the wrong way. All the hits that came out of those surrogate assays tended not to work on the natural. So if you are able to always use the natural substance that you are trying to potentiate or inhibit, So, let's see. I have a question here that says, does every GPCR supposed to have an allosteric site? That's a really good question, because in theory, any site on the protein can function as an allosteric site. If you believe that binding is not a passive process, then as you bind compounds to the protein, you're going to change their energy and their behavior. So it doesn't much matter where the compound binds, it will then become an allosteric site. So I would approach this by saying I don't know of a protein that hasn't got an allosteric site. You just simply have to screen and find them.
All right, good. So, hopefully you can all hear me now. David Winpenny of ARUK in Cambridge would like to ask what method or methods you would recommend for quantifying bias between signaling pathways.
Right, that's a good question. There have been several methods proposed, and there's actually a very interesting and very good review on this just recently published in Nature Signaling by Honoran and Costa, and they contrast all these methods. But in general, you can take the view that the main player in bias is efficacy, and so you just quantify the relative efficacy of compounds for different pathways. Or you can take the view that affinity is also involved. There is evidence that that it's probably a bit more cautious and relevant to do both. But the point also is, if we expect these numbers that we get from these nice in vitro simple assays to translate in vivo, we're probably ready for a heartbreak. All this does is it detects compounds that are different, exemplars. And so the translation of these numbers has not been very good when you try to then translate it to in vivo systems, because there's other things going on, receptor number and quantities of G proteins and all kinds of issues, temporal effects. These issues affect bias, and so the best thing you can do is use the simple assay to detect exemplars and then move those forward into the therapeutically relevant assays just as quickly as you can. There's not been much success in so-called modeling the therapeutic system. There's just too much going on.
Excellent. They're not going to catch you, are they? One more for you, from Hal Siegel from the New Amsterdam Sciences. Has the elucidation of intracellular endosomal signaling impacted the allosteric binding model, do you think?
Oh, yeah, that's really interesting. Well, anything that causes your receptor to behave differently to the host is an efficacy, and so you can have there is evidence now that some compounds will send the receptor into the cell, but the thing still keeps signaling. And the interesting aspect about all of this, whether it be beta-arrestin or G protein, cyclic AMP, or so forth, is the structure of the compound has to code for this. So something in the receptor active state, it'll go inside the cell, but for some states it will still continue to signal. So that it can just be viewed as one other aspect of bias. I mean, we tend to think about bias mainly in terms of G protein versus beta-arrestin, simply because those are the simplest assays. But bias really is a whole span. If you read the work of Luttrell, once the receptor goes in, beta-arrestin, there's different scaffoldings and different signalings, and it all has to be coded from the receptor active state. So, let me not get too far off your question. The answer is yes, it should be just considered another property, another biased signal, and then you start thinking, would this be useful therapeutically? Then you can quantify it and move on.
Excellent. Look, I think we can squeeze in one more, and that must be it, I'm afraid, guys. The question that I have got is from Sushan Wang, who is from Eli Lilly, and he would like to ask, the efficacy and affinity of agonists greatly depend on receptor density. How do you deal with this issue? Is it possible an agonist acting as a full agonist at one area, but as a partial agonist and partial antagonist at the other area?
Splendid question, and yes, of course, it's true. But I wouldn't... It's a question of naming things. In theory, affinity is supposed to be the equilibrium constant of the ligand-receptor complex. That is not going to change with receptor density. What you probably mean is potency, the concentration that does something. Yes, of course, that will. Efficacy as well should not change, but maximal response will change, and it's a function of. And yes, this is well known, and it really is an issue in translation. We will quantify a certain potency and maximal response in an assay, but there's no guarantee that as the compound goes in vivo, locates a host of organs with a range of receptor potencies and so forth, that you'll get a range of effects. However, we have ways to predict it. If we can get the Ka and the efficacy, we can actually predict that with a system-independent scale, and so that's why I stress using the right assay. So that is not quite the issue, except that depending on the pathway, we still don't know enough about which organs are coupled well and which organs aren't. So there's still some work there to do.
Okay, I'm going to push the boat up because it's almost Christmas. One more last question, definitely. This comes from Dietmar Krautwert from the Leibniz Institute for Lebensmittel System Biology. Are there examples for allosteric sites that partially overlap with the orthosteric site?
Good question. I would commend you to read the work of Arthur Christopoulos from Monash and his group. They pioneered this. There are compounds they're referred to as bitopic, and they actually formally have worked out from structure and so forth that these molecules actually do bind to both sites, and it confers upon these compounds special properties, and the whole issue is not so much what the compound does on its own, but what the compound does in concert with the natural system in vivo. An allosteric compound, as I mentioned, can be permissive, and so there will be a whole range of things that can happen. Orthosteric, there isn't. Bitopic, you sort of get a mixture, and it's a complex one with those, and so it's and there aren't enough of these compounds out there to forge general rules quite yet.
Excellent. Look, I think we have unfortunately run out of time. But for those who were asking the question earlier, please remember that the webinar will be stored on our website, and that is www.ddw-online.com. So that's ddw dw-online.com, and that'll be on demand certainly for the next 6 months, so you can click in, look at the slides in your own time, and obviously benefit from that. Once again, a big thank you to our speaker today, and thank you to our sponsor, Eurofins Pharma Discovery Services. May I also thank you, our attendees, and hope you'll join us for another DDW webinar in the near future. Thank you very much, and goodbye. Have a nice day. Bye-bye.
Bye.